Imagine this: a single electron, the tiniest building block of matter, shot at a wall. You expect it to behave like a bullet, a tiny point of impact, but instead, it paints a picture that defies every law of physics we thought we understood. And here's the real twist: the result seems to depend on whether or not someone is watching. This is the Double Slit Experiment, one of the strangest discoveries in all of science. An experiment so bizarre that even Albert Einstein struggled with it, and one that suggests reality itself may be shaped by the act of observation. Could human consciousness truly influence the laws of nature? To answer this, we need to go back 200 years, to when scientists were debating a simple question: what is light? Some argued that light was made of particles, tiny bullets streaming through space. Others insisted it was a wave like ripples on water. In 1801, a young English scientist named Thomas Young set out to settle the debate. He passed a beam of light through two narrow slits carved into a barrier. If light was particles, he expected to see two bright spots on the wall behind it. Instead, he saw something shocking: a series of alternating light and dark bands like stripes. This was a wave interference pattern. The bright bands showed where the waves reinforced each other, and the dark bands where they canceled out. Light, it seemed, was a wave. At least, that's what the world believed for the next century. But then came quantum physics. Einstein revealed that light behaved not only like a wave, but also like a particle, a tiny packet of energy called a photon. Physicists then asked a bold question: if light could behave as both a wave and a particle, what about matter itself? Could an electron, something with mass, do the same? To find out, they repeated Young's experiment, this time with electrons. A beam of electrons was fired at a barrier with two slits. Behind it, a screen recorded where the electrons landed. If electrons were simply particles, they would form two clusters behind the slits. Instead, the screen revealed the same interference pattern as waves. Each electron seemed to travel through both slits simultaneously, interfering with itself. This was shocking enough. But then they slowed the experiment down, firing electrons one at a time. Surely, a single electron could only pass through one slit. Yet even when sent through individually, the electron still created the same interference pattern. Alone, each electron behaved like a wave, exploring all possibilities at once. Only when it hit the screen did it collapse into a single position. The mystery deepened when scientists placed detectors at the slits to watch the electrons. This time, the interference pattern vanished. Instead of waves, the electrons behaved like particles, forming two neat clusters. The very act of observation seemed to change reality. Without measurement, electrons behaved like waves, existing in multiple states at once. With measurement, they chose a single path. Reality, it seemed, cared about whether it was being watched. Einstein hated this. He declared, God does not play dice. He believed there must be hidden factors we didn't yet understand. But Niels Bohr, one of the fathers of quantum mechanics, embraced it. He argued that quantum physics was about probabilities. Until observed, a particle exists in a superposition, a blur of possibilities. Observation collapses the wave into a single reality. This became known as the Copenhagen interpretation. But what counts as observation? Is it the detector or the human mind? Could consciousness itself shape reality? No one has ever fully answered these questions. And so the double slit experiment leaves us with a haunting possibility. Does the universe exist only when we look at it? And if that is true, who or what was watching before we were here? The double slit experiment opened a door that science has never been able to fully close. It revealed that the rules governing the quantum world are not the same rules we live by in our everyday experience. In our world, a ball is either here or there, not both. A car doesn't drive down two roads at once, but in the quantum realm, possibilities overlap. Reality seems to wait, suspended until a choice is made. This is the measurement problem, one of the deepest mysteries of physics. What exactly causes the collapse from possibility to reality? Some argue it is the measuring device itself. Others believe it requires a conscious observer. Either way, it challenges our notion of an objective, independent world. To highlight this strangeness, Erwin Schrödinger proposed his famous thought experiment in 1935. Imagine a cat inside a sealed box with a vial of poison, triggered by the decay of a single radioactive atom. If the atom decays, the cat dies. If not, the cat lives. According to quantum physics, until someone opens the box, the atom exists in both states, which means the cat is both alive and dead at the same time. Only observation decides the outcome. Schrödinger intended this as a critique, to show how absurd quantum theory sounded when applied to ordinary life. Yet the paradox still echoes. At what point does a quantum system choose a definite state? Decades later, American physicist John Wheeler took the mystery further. He imagined the delayed choice experiment. Suppose a photon is traveling toward two slits. If we decide to measure which slit it passes through, it acts like a particle. If we allow it to hit the screen freely, it acts like a wave. But here's the twist. What if we wait until after the photon has already passed the slits to decide how to measure it? Common sense says the photon's past behavior should already be fixed, yet experiments show the outcome still depends on the late decision. It is as though the particle adjusts retroactively, as if the future choice reaches backward to rewrite history. Stranger still is the quantum eraser variation. In this setup, scientists allow photons to pass through the slits, then mark information about their path. Later, they can choose to erase that information before the photon hits the screen. If the information remains, no interference appears. If the information is erased, the interference returns, even though the photon has already traveled. It seems reality can be reshaped after the fact, depending on what we choose to know. These experiments blur the boundary between past and present, between knowledge and reality itself. To make sense of all this, physicists develop different interpretations. The Copenhagen interpretation says the wave of possibilities collapses only when measured. The many worlds interpretation claims all outcomes happen simultaneously, but in separate branching universes. In one universe, the electron went left, in another, it went right. The pilot wave theory suggests particles are guided by hidden waves that determine their paths. Objective collapse theories propose the wave function simply collapses on its own after a certain threshold. And then, there is the most controversial: the idea that consciousness itself causes collapse. John von Neumann and Eugene Wigner argued that without consciousness, the universe would remain in a blur of possibilities. Only the mind crystallizes reality. Many physicists reject this, calling it mystical. They argue detectors alone are enough. But no experiment has yet resolved the debate. Could the human mind truly be entangled with the structure of reality? The question lingers. Einstein refused to accept such strangeness. He believed hidden variables must exist to explain the apparent randomness. He could not accept that reality was decided at the moment of observation. Do you really believe the moon is not there when you are not looking at it? He asked. For Einstein, quantum theory was incomplete. Yet despite decades of searching, no hidden variable theory has succeeded in fully explaining the double slit results. The debate remains unresolved. Meanwhile, quantum mechanics has proven astonishingly successful in practice. It powers lasers, semiconductors, computers, and the very screen you are using right now. The theory works with extraordinary precision, and yet its foundations remain shrouded in mystery. The double slit experiment is not just a curiosity. It is a mirror held up to reality, forcing us to question what existence truly means. Is the universe a fixed stage, existing independently of us? Or is it a shifting canvas, shaped by knowledge, perception, and choice? The story of the double slit experiment does not end with Schrödinger's cat or Wheeler's delayed choice. In fact, modern variations have only deepened the mystery. One of the most fascinating extensions involves a concept called quantum entanglement. Imagine creating two particles that are linked in such a way that their states are perfectly correlated. No matter how far apart they travel, measuring one instantly reveals the state of the other. Einstein called this spooky action at a distance. He could not believe nature would allow such instantaneous connections. Yet countless experiments have proven that entanglement is real. When combined with the logic of the double slit, entanglement leads to experiments that seem almost supernatural. In certain setups, measuring one particle can influence the outcome of its partner's interference pattern, even when the two are separated by vast distances. It is as though information travels faster than light, or perhaps bypasses space and time altogether. Some physicists interpret this as evidence that reality is not local. Events in one place can be instantly linked to events elsewhere, as though the universe itself is woven together beneath the surface. Others take it further, suggesting that retrocausality might be at play. Retrocausality is the idea that future events can influence the past. In some variations of the delayed choice quantum eraser, the decision to erase or preserve path information is made after the photon has already been detected. And yet the interference pattern responds to that later decision. It raises a profound question. Is the arrow of time as fixed as we think? Could the future reach back and alter the past? Such notions stretch the limits of imagination, but the experiments are real, and their results undeniable. The implications ripple outward into philosophy and even metaphysics. If observation determines reality, and if entanglement and retrocausality mean that choices here and now can influence outcomes across space and time, then what does that say about free will? Are we making choices? Or is the universe playing out a grand design where past, present, and future are entangled in ways we cannot comprehend? Some scientists argue that what we call reality is not fundamental at all. Instead, they suggest that the universe is essentially information. Particles, waves, matter, and energy are all secondary to a deeper layer of reality composed of data and relationships. In this view, the double slit experiment does not merely reveal a quirk of physics. It is showing us that reality itself is like a computation, a cosmic code unfolding in mysterious patterns. This interpretation has fueled speculation about the simulation hypothesis, the idea that the universe itself could be a vast simulation with rules that glitch under scrutiny. When electrons behave like waves until observed, is that simply the code rendering reality in real time? Mainstream science remains cautious, but the parallels are striking.
Another frontier involves quantum mechanics in the human brain. Some researchers have asked whether consciousness itself might arise from quantum processes within neurons. If the mind is partly quantum, then perhaps the strange dependence of the double slit experiment on observation is not a coincidence. Perhaps the observer is more deeply entangled with the observed than we realize. Critics dismiss this as speculative, pointing out that the brain is warm and wet, not the kind of environment where fragile quantum effects usually survive. But others counter that life itself has evolved ways to harness quantum phenomena. After all, photosynthesis in plants, navigation in birds, and even certain biological reactions appear to rely on quantum effects. If nature has already integrated quantum mechanics into living systems, why not consciousness? The possibility lingers like a shadow, that our minds are not simply watching reality unfold, but are participants in shaping it. The double slit experiment thus becomes more than physics. It becomes a mirror reflecting the deepest questions we can ask. What is time? What is space? What is consciousness? Are we beings moving through a universe? Or are we threads in a single interconnected fabric that creates itself as we look? These questions remain unanswered, but each new experiment reminds us of how much we still do not know.
The double slit experiment has been repeated countless times in labs around the world, with photons, electrons, even molecules made of thousands of atoms. Each time, the mystery persists. Particles behave like waves of probability until they are observed. Then they snap into a definite state. Reality seems to withhold its choice until the last possible moment. It is a result so strange that Richard Feynman once said it contains the only real mystery of quantum mechanics. And yet this single experiment has built the foundation for technologies that shape our lives. Lasers, computers, smartphones, quantum cryptography, all emerge from the same physics that refuses to make sense. The paradox is unavoidable. Quantum mechanics works flawlessly, but nobody truly understands why. Some scientists argue that perhaps our demand for explanation is the problem. Maybe nature simply is this way. Perhaps reality does not owe us comfort or intuitive rules. Others insist we are missing a deeper theory, a hidden order beneath the chaos. The debate rages on. Beyond science, the experiment has seeped into philosophy, spirituality, and even pop culture. The idea that reality might depend on observation has been taken to extremes, suggesting that the mind, or consciousness itself, is not just a passenger in the universe, but a creative force. If true, this would redefine our place in existence. We would not simply be observers of reality, but participants shaping it with every act of awareness. But can this really be so? Mainstream physicists remain cautious. They emphasize that the experiment does not prove consciousness controls reality, only that measurement matters. Yet the line between measurement and awareness remains blurry. What is measurement, if not information being registered? And what is consciousness, if not the experience of information? The questions spiral without end. In modern labs, researchers are pushing the boundaries further. Quantum computers exploit superposition to perform calculations that would take classical machines millions of years. Entangled particles are used to create unbreakable codes. Even attempts to link quantum mechanics with gravity, the holy grail of physics, sometimes turn back to lessons from the double slit. The experiment remains a guidepost, a reminder that the universe is stranger than we dare imagine. And then there is the question of scale. If a single electron can exist in multiple states until observed, what about larger systems? What about us? Could it be that entire realities hover in superposition, branching and collapsing as choices unfold? If so, then every decision you make could be splitting the universe into countless possibilities, each as real as the one you experience now. It is a dizzying thought, a multiverse of endless versions of you, born from the same quantum rules that govern an electron. Whether or not this is true, the experiment forces us to rethink the solidity of the world. It asks us to see reality not as a fixed stage, but as a shifting tapestry woven from potential, chance, and observation. And so we arrive at the heart of the mystery. When you close your eyes, does the world still exist exactly as you left it? Or does it wait, suspended, until you look again? Is the universe an objective reality? Or is it more like a story that requires a reader to come alive? The Double Slit Experiment offers no final answer. Instead, it leaves us with an open door, an unsolved riddle at the core of existence. Perhaps one day, a deeper theory will reveal the truth. Or perhaps the mystery is permanent, woven into the fabric of the cosmos itself. Until then, we are left to wonder. Are we living in a universe that exists independent of us? Or are we, in ways we cannot yet fathom, the authors of reality itself?